Hi, in this video, I'm going to go through OCR A-level Chemistry paper. This is the 2019 paper, and this is paper 2, the organic chemistry part of the specification. Okay, I'll start off with the multiple choice questions. Which alkane has the highest boiling point out of those? Well, I think if you check, they've all got 7 carbons, they're all saturated, they've all got the same molecular weight. So which one is going to have the biggest London forces? Well, it's going to be A, because that is the straight chain one, and of course with straight chain alkanes, you have more surface area, effectively more points of contact. All of the others, these are all branched, so you have the same number of electrons, so potentially the same strength of London forces, but they're not as strong because they have fewer points of contact. Okay. Number 2, butane reacts with chlorine in the presence of ultraviolet, okay, which shows a propagation step. Right, so a propagation step, you need to have a non-free radical species reacting with a free radical to make another free radical. Okay, so you can see that this one is actually initiation, isn't it? This one, 2 free radicals coming together, B, that's termination. D is a free radical propagation step, but you don't usually get that radical form, so it's not that one, but it is this one, the chlorine free radical reacting with this non-radical to form a different free radical, and HCl. D is the correct answer. Right, name the compound below. So we need to find the longest carbon chain, and we need to include that alkene group in the longest carbon chain. So the other 1, 2, 3, 4, 5, 6. So that's going to be hextuene. But we've also got this side group stuck on it, which is an ethyl group. So we'll call that 3-ethyl hextuene. So that C is the right answer. 3-ethyl hextuene. Right. We've got a stereoisomer shown below. Which term correctly describes a stereoisomer? Right, now you've got non-rotation around the carbon-carbon double bond, which is why it can show stereoisomerism. Now we shouldn't be using the terms cis and trans. You can only really use them when you have when you have the same groups attached to the carbon. So we should be using E and Z. Okay, so which one is it? Is it the E or the Z? All right, let's look at this blue carbon here, the highest priority group. So that is the one with the biggest molecular weight, essentially, which is that one there. And this green carbon is more tricky. Okay, which is the highest priority? Because they've both got the same, these have both got 3, they're both C3H7. So which one is the highest priority? Now the rule here, well, it is actually that one, because what you should do is, if I just draw them, that is this one here. And the top one would be like this. The first thing you do when you're assigning priorities, you look at the first carbon there, and they've both got one, the first atom, that's a carbon, that's okay, and then you look at the second one. All right, and the second one, right, you see what is attached to this first carbon. Now, attached to this first carbon, you've got 2 hydrogens, whereas attached to this carbon here, you've got 2 other carbons and 1 hydrogen, and the carbons are heavier than that, so that's why this counts as the highest priority. So the 2 high priority groups are on opposite sides, so that is the E isomer. Okay, which type of bonds are broken and formed in the reaction of ethene and bromine? Let's just draw that. So we've got ethene. It's going to react with Br2 to form dibromoethane. So what kind of bonds are we breaking then? Right, we're breaking that, which is a pi bond, and we're breaking that, which is a sigma. So we want pi and sigma so it's got to be C or D. Which kind of bond is formed? Well, we're forming these 2 bonds here, and they're both sigma bonds. So that is the answer. D is the answer there. Question 6. What is the organic product of the reaction below? Okay, so we have got potassium hydroxide in aqueous solution reacting with that. Now, it will replace, you will get nucleophilic substitution with this chlorine because it's attached to an alkyl group, but you won't get nucleophilic substitution with that because it's attached to the benzene ring. So we're just going to replace the top chlorine there. So the answer is A. That's what's going to happen there. The hydroxide can't react with the benzene ring. Obviously, D is wrong. Okay. Okay, what's the number of chiral carbons shown in the steroid molecule below? So we need 4 different groups attached. Well, I'm going to color all these are all CH2s. That's a CH2, so these aren't chiral. Okay. That's a CH2, that's a CH2. They're not chiral. Okay. I'm going to color in, these ones can't be chiral because they've got double bonds, so they're only attached to 3 things. Forget about them. I'm going to color that one in there. That's a CH3 group, so that's not chiral. It's got 3 hydrogens attached. Now everything else there has got 4 different groups attached. So we have got there, we've got 1, 2, 3, 4, 5, and 6. B is the answer there. Okay, phenol reacts with bromine, which is the least likely organic product. Right, now when you get electrophilic substitution, so basically you swap the hydrogens on the benzene ring for bromine atoms, but you should know that with phenol directs, we say it is 2, 4, 6 directing. So that's carbon atom number 2, number 4, and number 6. It tends to add the bromine on those positions there because you've got higher electron density there. So electrophilic substitution occurs more readily. So A is okay, they're in the right places. B is okay. C is wrong because this bromine here is on carbon number 3, and that tends not to get, you tend not to get substitution there. So C is the answer. This is R1. And D, of course, is okay because you've got 2, 4, and 6 there. Okay, it's a polymerization of polyester. Which monomers could form this polymer? Okay, so it's a polyester, I think. So you're going to see that what we are, the monomers, the ester linkage has been formed there. Okay, so you can see you have got, and also there is a repeating unit, you've got a dicarboxylic acid here, this thing, and you've got a diol with 2 carbons in it there. Right, there's a diol with 2 carbons, that's good, and this is the dicarboxylic acid with 4 carbons in it, so that the answer is A. B, you've got the right carboxylic acid in B. It's the same, they're just drawing it the other way around, but this alcohol's got too many carbons in it. That's got 3 carbons. This alcohol's got 3 carbons, so that's wrong. And D is completely wrong because it's not formed from a hydroxy carboxylic acid. It's from a dicarboxylic acid and a diol. All right. Number 10, which compound shows 4 peaks in the carbon-13 spectra? So we need 4 different carbon environments. Okay, so if there's quite a bit of symmetry in this first molecule. So we look at that's going to be that one and that carbon are the same. That one's unique. That one is the same as that one. That one's the same as that one, and that one's unique. So that's got 5. So it's not that one. Let's look at the next one. Right, that one is the same as that. Those 2 are the same. Those 2 are the same, and those 2 are the same. So that's got 4 peaks. B is the answer. Just check that the others aren't right. Okay, so if we look at C, you're going to have that one is unique. That one is the same as that. Those are the same. And you've got 4. So C is going to give you 5 peaks. And D is very symmetrical, so you're going to have there, you're going to have that one is the same as that one is the same as that, and these are all the same. That will only give you 3 peaks. Okay. All right, a percentage yield question here. Right. Okay. So we are going to make the secondary amide from the amine. Right. So 1 mole of the amine gives us 1 mole of the product. Okay. So let's work out the moles of this stuff. Okay. Phenylamine. C6H5NH2 is equal to mass over MR. 4.5, they tell us the MR is 93. That gives us 0.0484. So that means we should get how many moles of the secondary amide? Twice like that. It should be the same. If we get 100% yield, that's 0.0484. So therefore the mass we're going to get is equal to the moles multiplied by the MR, 0.0484 multiplied by the MR, they tell us is 135. That gives us 6.53 grams. Okay, so the percentage yield is going to be what we do get, which is 3.25 over what we expect, 6.53 multiplied by 100 gives us 49.8%. So A is the answer there. Quite straightforward, but quite time consuming. Okay, 12. A compound produces the 13C NMR spectrum below. Which compound could have produced this spectrum? Right, you've got 3 peaks here. We don't really need to look at the chemical shift. I think we just need to look at the number of environments. Well, let's look at propane. Propane, of course, is like that. So these 2 N carbons are the same. So propane is only going to give you 2 environments, so it can't be that. Methyl butane, right? I'll just draw the skip. Let's just draw it like that. Methyl butane, how many peaks are we going to get there? Well, that's going to give us 1. They're the same. 2, 3, 4. So it can't be that one because there's only 3 peaks. 2 methyl propan 1-ol. Okay, let's draw that. 2 methyl propan 1-ol. So put the OH there. Okay, we've got these 2 carbons are the same. That's different, 2, 3. That would give you 3 peaks, so that's a possibility. Let's just check that D can't do it. 2 methyl propan 2-ol. There's only 2 peaks in that one. So with the OH on carbon atom number 2, you can see there that all of these carbons are the same, and that one's different, so that would give you 2 peaks, sorry. So C is the only one it could be there. You don't need to worry about the chemical shifts. Okay. Right, a carbonyl compound reacts with NaBH4. Which compound could be formed? Right, now what does this do? Right, it will reduce a secondary. It will reduce a ketone to a secondary alcohol. It will reduce an aldehyde to a primary alcohol. Okay, so you can't get tertiary alcohols by reacting with NaBH4. So what we need to do is we need to look at, we haven't got any tertiary alcohols there. Methyl pentan 2-ol. Let's look at that one. Okay, we've got 5 carbons, 2 methyl pentan 2-ol. That's a tertiary, so you can't form that one. Let's look at 2 methyl pentan 1-ol. Put your methyl there, and your OH there. That is a primary alcohol, so that is okay. 3-methyl pentanetol, finally. Let's draw that one. That's a secondary alcohol, I think. So methyl, 3-methyl, beg your pardon. A methyl on carbon number 3. And we have got the alcohol on number 2. That's a secondary alcohol, so that's okay. So it's 2 and 3 as the answer. So C is the answer there. Number 14, which chemicals can react with phenol? Okay, right. Right, so phenol, can it react with potassium hydroxide? Well, it can, because that H, unlike an alcohol OH, this H can be removed, because then you end up with the negative charge on the oxygen, and that can be partly delocalized on the benzene ring, which stabilizes it. So yeah, it can react with that. Can it react with ethanoyl chloride? Yeah, they can. You're going to get acylation there. It can react there to form an ester, and you lose HCl. Yeah, it can do that. Can it react with nitric acid? It can. You can get electrophilic electrophilic substitution occurring with just nitric acid, because benzene, it won't do it, but of course the phenyl group activates the benzene ring, makes it more reactive because it puts electron density into it. Yeah, so you can have that. So 1, 2, and 3 are all correct there. A is the right answer. Right, I think this is the last multiple choice question now. Yeah, it is. Okay. So we've got a compound there used to treat influenza. Which functional groups are in a molecule of the compound? Right, have we got an ester linkage in there? Yeah, we have. We've got one there. Have we got a secondary amide? Yes, we have. We've got that one there. And have we got a ketone? No, there's no ketones there. Those carbonyl CO groups are both involved in the ester, the secondary amide, so no ketone. So 1 and 2 is the answer there. B is the correct choice. Right, question 16. Unsaturated aldehydes and alcohols. This is about, okay, so we've got this compound that's used as a food flavoring. We've got a carbon-carbon double bond, and we've got an aldehyde group in there. Right, 3-methyl, the compound reacts with HBr. So which functional group is going to react with the HBr? It's the carbon-carbon double bond, forming a mixture of 2 organic products. One of the organic products forms in much greater quantity than the other. Outline the reaction mechanism for the formation of one of the products. Right, I'm going to show for the formation of the so-called major product. Okay. The same mechanism essentially though. Right, so let's do that. Now, what is the reaction mechanism? HBr, it's electrophilic addition. So we need to have our HBr. Actually, let's do it in green. Right, there's a dipole on that molecule because bromine is more electronegative, delta minus, delta plus. That makes that hydrogen an electrophile. Okay, so the first step in the mechanism is for the pi bond to break, the pair of electrons move on to the hydrogen, form a bond with that, and at the same time the hydrogen-bromine bond breaks. Let's draw the intermediate. This is 4 marks, by the way, just rub that out. So we are going to get, and I'm going to show the hydrogen sticking on to this carbon here. Talk about that in a minute. We've still got our aldehyde group there and H there. That means that this carbon has got a positive charge on it. It's a carbocation, and we have Br minus. That incidentally is a tertiary carbocation, which is more stable than the secondary carbocation. That's why you get the major product, but it doesn't ask us that. Here's our bromide ion. The final step in the mechanism is for that to go to there, and then you form the product. And we've got a BR on there and an H on there. Okay, that is our product. Right, now the next question is explain why one of the organic products forms in much greater quantity than the other. Right, so I've drawn those two structures in blue there to sort of illustrate that. Right, let's draw let's draw the major product on the left. So what happens is you form, I'm going to explain it with these diagrams. So we've got CH3 there, and we have that is the carbocation intermediate, and that is a tertiary carbocation. To form the minor product, what happens is you stick the hydrogen on the other carbon, so it sticks there. And we've got the carbocation there. That is a secondary carbocation, which is less stable than the tertiary, so it doesn't form as much. And then just to show the two products, so this product which comes from the tertiary carbocation, the bromine on that carbon there, that's the major product, and the minor product will be with the bromine on this carbon because it reacts with the carbocation, and that is the minor product, this one, because it is formed through the secondary carbocation, which is less stable than the tertiary, so it is less likely to form. You don't really need to draw all those diagrams out in your answer. It's only 2 marks, you probably wouldn't have time to, but I've just done that to sort of explain. You just have to say that the major goes through the tertiary carbocation, the minor through the secondary, and the tertiary is more stable than the secondary. Okay, so you've got 2 isomers in citronella oil. They are structural isomers of each other, and they also show stereoisomerism. Describe how the observations from a chemical test would distinguish geraniol from citronellal. Right, well, this one here has got an aldehyde group, okay, and there's no aldehyde group in the other one. So you can use that to distinguish them. Test for an aldehyde, you can either use phalins or toluenes. I'm going to say phalings test. Okay, so phalings test. You get a blue solution, forms a brick red precipitate with citronellal, but it won't with geraniol. Okay. Right. What is the molecular formula of geraniol? Right. So let's count up those carbon atoms. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So it's going to be C10. Now, if it was saturated, it would be the number of hydrogens is 2n plus 2, so that would be 22 hydrogens. But it's not going to be 22 because it's got 2 double bonds. So we subtract 2 hydrogens and then another 2 for the second one, 18. So you've got 18 hydrogens there, and you've got just 1 oxygen. So C10H18O. And you can do that more slowly by counting up the hydrogens if you want. Okay, what is the molecular formula of geraniol? Sorry, you've done that. Explain why they are structural isomers of each other. Well, the old definition that you just should know, you just got to say same molecular formula, but different structural formulae. Okay, so that is straightforward recall. It was asked that on AS papers quite a lot as well. Explain the term stereoisomerism. This is another definition, and they ask this quite regularly. So I would say the same structural formula. But different arrangement of atoms in space or groups. That's good enough for 1 mark. Okay, that's the definition you should always use, really. Okay, the structures of geraniol and citronellal are repeated below with the carbon atoms numbered. Explain the types of stereoisomerism shown by the 2 molecules. Okay, so stereoisomerism, we've got to think of 2 things. We've got to think of isomerism, and the other kind of stereoisomerism, of course, is optical isomerism. Right, so in your answer, refer to the numbered carbon atoms and above and draw diagrams showing any stereoisomers. Okay, so let's look at geraniol first. Now there are no asymmetric carbons in there. There's no carbons with 4 different groups attached. So it's not that. So it's got to be EZ isomerism. Let's look at this double bond here. Right, now that there's no stereoisomerism across that, because you've got a methyl group there and a methyl group there. You've got 2 things attached to the same carbon. So we can forget about that double bond. Let's look at this one, the one between 2 and 3. And there is EZ isomerism there, you can probably see. Right, if we have a look here, we have got between 3 and 2, looking at this one, we've got a methyl group there, and we've got this higher priority group there. And attached to carbon number 2, well, we've got a hydrogen. I'll just draw on there. And this higher priority group, okay, this CH2OH group. So the 2 high priority groups are on opposite side. That is the E form. So I need to draw the Z form. I need to draw a diagram showing a stereoisomer of that. So let's draw that. So just got to be careful copying this structure. I draw it right. So double bond. Here is the double bond that shows stereoisomerism, right? So I'm going to draw it the other way around to that one there. So instead of going up like that, I'm going to put it like that there. Okay, so that goes down. That's carbon number 1, and then we have an OH on that. Okay, so that's the stereoisomer. That's the Z isomer. Citronellal. Now let's look at this. You don't have any EZ isomerism in this molecule, because again, this one here, you've got 2 methyl groups attached. So they're 2 carbons, 2 identical groups attached to the carbon of the double bond. So no EZ. You can't have EZ with this one here. It's not carbon-carbon double bond. So have we got any optical isomers there? Well, if you look at carbon number 3, you can see carbon number 3, rub that out. Carbon number 3 is asymmetric. It's got 4 different groups attached. It's got carbon number 4, carbon number 2. It's got a methyl group up there, and it's got a hydrogen attached here as well. Okay, so how are we going to draw 2 stereoisomers of that? Well, they are non-superimposable mirror images. So what I'm going to do is I'm going to draw one. There's our asymmetric carbon. I'm going to draw the hydrogen there. So I'm going to draw the hydrogen coming out as a wedge, coming towards us to show the 3D arrangement around there. And then we've got that. 1, 2, 1. Okay. Now I'm going to draw the mirror image of that. So there's my mirror. I just have to be careful to draw the mirror image of it. So I'm going to have the oxygen there. Here's our asymmetric carbon there. And that's our double bond. Okay, so they are these two things are non-superimposable mirror images of each other. They are optical isomers. Quite a lot of drawing there for just 2 marks, I think that question was. Yeah, okay. Right, question about amino acids, okay. There's the general formula of the amino acids, and there is the R group, which is shown for 4 different amino acids. Right, but this question is just about, this first bit is just about the amino acid serine. So in the boxes, draw the organic products for the reaction of serine shown below. Right, so they've drawn serine for us here in 3D, 3 displayed formula, sorry. We've only got 3 products. We've got 4 marks here, so they probably let us, there's probably one of these structures that you're allowed 2 marks for. Right, so let's talk about the acid first of all. Well, what's acid going to do? It's not going to touch the carboxylic acid group, but it is going to protonate that. It's going to turn that into an NH3+. So that's going to be just NH3. It's going to protonate that. And the rest of the structure, I won't draw all the structure, save time, but the rest of it's going to be the same. And don't think that it's going to protonate the OH, because it won't do anything to that. It's just the NH2. That's the only basic group there. Right, now this one here is how does it react with sulfuric acid catalyst, and this is actually propan-2-ol, an alcohol. Right, you've got a carboxylic acid group there, and that is going, with an acid catalyst and an alcohol, you're going to form an ester. So let's draw the ester there. I'll draw it outside the box. There's a bit more room. Right, so you're not going to touch these. Oh, the sulfuric acid, actually, you are going to protonate that, aren't you? So maybe that's what that second mark's for. So I'm going to put that as plus there. Nearly forgot that. Okay, and then you're going to get CH2OH there. You have got your, which is propan-2-ol, the ester. So you get there's the, there we go. So you can see there, I'll just draw a circle around it. That's basically the propan-2-ol bit. Yep. Okay. So that's the ester you're going to form there. And then finally, how is it going to react with excess acyl chloride? Now, acyl chlorides will react. They won't react with carboxylic acids, but they will react with amino groups. It will acylate it to make a secondary amine, and it will also acylate the OH group to form an ester. Okay, so you're going to get two acyl groups attaching there. So let's draw that. You're going to get so right here is our, we've now acylated that acyl chloride, so we stuck on the ethanoyl group. Likewise here, we're going to do the same there. And the rest of the molecule, the carboxylic acid bit, stays untouched. So there we can see we've stuck on 2 acyl groups, one there and one there. And of course, you get HCl released for each of those reactions. Okay, so a fairly typical question about amino acids, and all you've got to do, remember, is you've got 2 functional groups, or in that one you've actually got 3 functional groups in the same molecule. You just treat those functional groups separately. You know, there's nothing special about them because they're in the same molecule. How do they behave? How would they behave separately? And extrapolate that. How do they behave when they're in the same molecule? Okay, so here's a calculation one. A student is provided with one of the 4 amino acids. I've drawn a little diagram here to show what they've done. They carried out titration with the standard solution of hydrochloric acid to try and identify the amino acid. Okay, the method is outlined below. So they get this much of the amino acid and they dissolve it in water, make up a 250 centimeter cube solution of it, put that into the burette here and titrate it against 25 centimeters cubed of hydrochloric acid. We know the concentration of that. Now, we need to look at those. How do amino acids react with HCl? Well, let's just draw an amino acid. We've said it's only the NH2 group that is going to react. Right. So there's our amino acid. We're going to how does that react with HCl? It reacts in a 1-to-1 ratio because we just protonate the NH2 group. But we have to be a little bit careful here because some amino acids contain NH2 groups in the R group. Okay, so we have to just check that there's no NH2s in that R group. So let's look at the original table again. I'm going to paste this original table. Okay, so the original table, here we go. I'll copy that. You can see that none of those R groups contain NH2, so they're not going to react with the acid. So it is a 1-to-1 ratio of the amino acid with with HCl. Okay, so it's a 1-to-1 ratio. So first of all, we've got to find out the moles of HCl. We can do that because we know the concentration and the volume. So let's do that. So moles HCl, conc times volume. So that's 0.15 multiplied by 25 over 1,000, volume in dm cubed, of course. That gives us 3.75 times 10 to the minus 3 moles. Okay. Okay, so that means we know that that's going to react with the same number of moles of the amino acid. Okay, and so we know that in that volume, that title of the amino acid, we've got that many moles. So let's write that down. So in 21.3 centimeters cubed of amino acid solution, we have 3.75 times 10 to the minus 3 moles. Right, so what we're going to do now is work out the concentration of our amino acid solution. Let's do that. So the concentration of the amino acid is equal to moles over volt. And if we know the concentration of the amino acid solution, what we're aiming for is to work out the number of moles we've got in that 25 centimeters cubed. We know the mass of that. So we know the moles of the amino acid. We know the mass. We can work out the MR of the amino acid. We know the MR, we can identify it. Okay, so concentration of the amino acid moles over volume. So 3.75 times 10 to the minus 3. The volume was 250 centimeters cubed. That's 0.25 dm cubed. That gives us a constant. Sorry, it's not that at all. That's in the titer, which is 21.3. Okay, so that's 21.3 over 1,000. That gives us a concentration of 0.176 moles per decimeter cubed. So now we're going to find out the moles of amino acids in 250 of solution. That is going to be, so the concentration times by the volume, 0.176 multiplied by the volume, which is 0.25, that's 250 centimeters cubed and dm cubed. That gives us a number of moles of 0.0440 moles. Okay, so we know the moles and we know the mass of that amino acid. They told us, okay, it was 5.76766 grams. So let's work out the MR of the amino acid is equal to the mass over the moles. The mass we had was 5.766 and the number of moles is 0.044. So that is going to give us a total number of, that gives us an MR of 100 131. So now we have to find out which of those amino acids is going to have an MR of 131. So right, I'm going to move over here, so I've got some space. Just paste in that table there. There's our amino acids. Okay. Right, so I'm going to draw an amino acid and work out. So the general formula for an amino acid, of course, is, so we have a carbon atom, a carboxylic acid group, an H, and NH2 group there. I just draw it like that, even though you shouldn't really do that, and an R group. Okay, so let's work out how much does all that lot weigh. Right, that lot without the R group, so it's 14 for the nitrogen, plus 2, plus another 1, plus 12 for the carbon, plus 12 for that carbon, plus 32 for those oxygens and 1 there. That gives us 74. That weighs 74. So we know in this case the whole molecules weigh 131, so R group is going to weigh 131 minus 74, which is equal to 57. Okay, so which of these R groups is going to weigh 57? Well, it's not going to be, obviously not going to be glycine because that only weighs 1, so it's not that. It's not going to be alanine, that weighs 15, CH3. Serine, that's not going to be 57, it's going to be too small. But what we've got there is we have got C4H9 there in leucine, and of course that does weigh 57. So the answer is the amino acid was leucine. Right, okay, so now we're going to look at the amino acids with some TLC chromatography. Okay, so what is the RF value of serine in solvent W? Okay, right, so I'm going to have to use this. What is RF? So RF is equal to, the RF value is the distance moved by the spot divided by the distance moved by the solvent front. So, right, I've got our, the ruler's not going to play, I don't think. Right, it is. Let's move it over. So it's the, what have I, it's got to do it for serine. Okay, so let's move it over there. Right, okay, how far is that solvent moved then? Okay, let's start off there. That's 1 unit on the ruler. That's 2.25 units of the solvent's moved, I think. And how far has the spot moved? Well, it's moved exactly as the serine. Right, it's there, isn't it? Which is about, that's 0.9. So 0.9 over 2.25. Obviously, this is much easier to do on paper. So we might not get a very accurate answer. 0.9 divided by 2.25 is 0.4. Okay, so 0.4 is the RF value there. Right. Now, analyze the chromatograms to identify the unknown amino acids for 2 marks. Okay, so let's look at in solvent W first of all. This one on the left. Right, now the unknown amino acid moves up to here. So it moves almost exactly the same as leucine and glycine. So we don't know whether it's leucine or glycine. But when you put it in the other solvent, let's look at leucine and glycine. Well, it doesn't move the same as leucine. Leucine moves much further in that solvent, whereas the glycine moves the same as our unknown. So our unknown has got to be glycine. And you wouldn't be able to identify it was glycine from just either of those chromatograms. You've got to use both. I say that is if you look at the unknown, if you just look at this solvent here, well, if you just looked at that alone, you might think that it was either alanine or glycine. So you do need both of them. Right, now that's about halfway through the paper, so I'm going to call it a day there.